Okie dokie. So, notes, this is week 3, part 1, and we're talking about motion. So we will just sort of talk through some questions and think about them, and then we're going to learn about some equations. But I do like you to understand what's going on before we simply randomly grab an equation, start plugging in numbers, hope we get a correct answer. So, if Joey goes a speed of 4 meters per second, meaning every second he travels a distance of 4 meters, for 5 seconds, how far does he go? So what I'm always recommending is that students, meaning you all, let's see, draw a diagram. So here's our Joey, and Joey goes, so I might do like there's 4, and there's 4, and there's 4, and this might really help it make sense. So this would be 1 second. And so again, this, if you're like, hey, I know the answer is 20, this looks like a lot of work. Yeah, but I'm just trying to help this make sense. So we build an intuitive understanding. So Joey here goes a distance of 4 meters in that second, 4 meters in this second, 4 meters in this second, etc. And so counting them up, you see that Joey travels a total distance of 20 meters. So that would be our answer. All right, 4 meters every second for 5 seconds. Notice how we didn't use a formula there. Very nice. Number 2, if Joey has a velocity of -4, meaning moving in the opposite direction for 1 minute, how far does he go and in what direction? So I'm not going to draw it all out. That would take forever. But it'd be something similar where we have, there's a distance of 4 meters and here's a distance of 4 meters, and each of these is 1 second. And over the course of 1 minute, we know we have a total of 60 seconds. So if he's traveling 4 meters every second for 60 seconds, we know he goes a total distance of, what is 60 times 4? 240 meters, and that would be to the left. You could say to the left, you could say in the negative direction, you could say west. It's all good. Number 3, if Joey starts at a position of 50 meters and goes -2 meters per second for 2 seconds, what is his final position? All right, so we're given some position, and you can imagine this is a position of 0. And so way out here, we have a position of 50 meters. Notice that's in the positive direction. And Joey's going -2 meters per second. Joey again, meaning 2 meters every second to the left. So something like this. I'm drawing little arrows. Each of those arrows might be 2 meters every second, and he does that for 2 seconds. So he did this. He went 2 meters and then another 2 meters. So we went from 50 down to 48 meters and then down to 46 meters. And so his final position is where he ends up. So that would be 46 meters. All right, so again, we're solving these without equations. We're drawing diagrams. We're thinking about it, and we're trying to build our understanding of what does that mean. Goes -2 meters per second for 2 seconds. Question 4, using slope-intercept form, blast from the past, y equals mx plus b. Try to write an equation for final position in terms of initial position, time, and velocity. So if we had something like this, so this is position, and this is time, and we had a line like that. So you're definitely familiar with y equals mx plus b, where b is the y-intercept and m is the slope. And from last week and the week before, you know that the slope, when we have position and time graph, we know that the slope is, you guessed it. Sorry my writing is so messy here. I'm using a different device. Slope is velocity. So I'm going to write that in here. M equals velocity. So that's rate of change of position with respect to time. So if we were writing this out, we're looking at what we're talking about. So by position, we mean the y value. So you could say something like position, and we're going to use x as our variable. And I know that's totally weird because here this is position, but we're using x. And then slope is velocity. So where's my marker? Velocity. And then the x-axis for us is time. So marker, there we go, time, plus, and what's our y-intercept? Our y-intercept is our initial position. So when we see an equation like this, this is telling us that position, or final, let's put this in our notes. Final position equals, this is velocity, and this only works if the velocity is constant. If the velocity is changing, then we have some acceleration to factor in. And don't you worry, we'll get there. Time and initial position. Initial position. So to tell you the truth, which of course I always do, this is no different from distance equals rate times time, which you learned in 3rd grade or whatever. And that's this right here. Distance equals rate times time. We just, fancy it up for AP Physics, and we throw in the fact that the object, the person, may start in some location other than 0, in which case the distance, their position is different from the actual distance they've gone. So this, what is this? Is this Joey? Oh, we don't know. Okay. So this is the distance they've gone, but notice how their final position is different from the distance they've gone because they did not start at 0. Cool. I think that makes sense. Let us invest. All right. So let's take a look at page 2. This different device, I don't know, something happened with the recording, so hopefully this worked. So when something is accelerating, using distance equals velocity times time doesn't work because the velocity is changing. So I have an example here of a velocity and a time graph. And so we have the velocity is positive and increasing, and then positive and decreasing. So a roughly sketched position time graph, we have x position versus time, might look something like this, where it starts at a slow speed, speeds up, speeds up, speeds up. That would correspond to this location. And then slows down, slows down, slows down, but always has a positive velocity. So the velocity always has positive. It's never down here. So when we do, for a constant velocity, distance equals velocity times time, consider this little graph, a velocity time graph. We can basically multiply velocity by time, and that's kind of like finding the area of this rectangle. And that gives us the distance traveled. So we can find the total distance traveled when the velocity changes like this by finding the area under the graph. So this shaded area, if we had numbers here, would, if you calculated it, would give you the total distance traveled. So it's like you're doing velocity times time, but because the velocity changes, it ends up being the area, so it'll be like triangles, trapezoids, rectangles, that kind of thing. Okay, key concept there. So we're talking about equations of motion, and on the previous page we talked about this one. Position equals velocity times time plus initial position. So make note that that is constant velocity only, that says in my messy writing. If the velocity is not constant, we need an acceleration term. So notice how this equation is basically this equation, except we now have this acceleration term, and the velocity, because it changes, we've described this as initial velocity, or v sub 0 or v naught. Okay, so let's pay attention to what these actually are. So this is, we have final velocity initial velocity, acceleration. The acceleration, we will always deal with constant acceleration situations. So that's acceleration, and this is time. All right. And we have our terms defined here, basically. Acceleration, time, initial velocity. Let me point at those, sorry. Acceleration, time, initial velocity, initial position. I'll write that in. Initial position and final position. Hey, what was that? Okay, sorry. And final position. All right, looks good. And so this, our equation that doesn't involve time, we like this one. This is, again, final velocity. Final velocity. Same thing, initial velocity, acceleration, and this is, I'll write this out because this will be helpful if it's spelled out for you. So we have final, oh, that worked, minus initial position. In other words, final minus initial position is displacement. Displacement. All right. And if we're finding average velocities, so this right here, marker, average velocity, and as defined above, final velocity, initial velocity, and just take the average of them, meaning add them together and divide by 2. Okay, and then you should also have on this page, we've talked about like average speed and average velocity. So let's say average speed is total distance. I'll say total, that's a total distance over total time. And average velocity was different from average speed in that we were talking about the total displacement. Displacement over time. All right. So I'm using my tablet and not the iPad, which is why the writing is so messy and these weird windows keep popping up. Hopefully this works. The iPad's taking more than an hour to process videos, so I'm kind of having an epic. Thanks for listening.